In this lecture, we're going to discuss running water. So first, we're going to put running water in perspective on the planet. So how much of the water on Earth is running water, and what exactly is running water? So here's the hydrosphere, this entire pie chart, and this includes all the water on the surface of the Earth, below the surface of the Earth, and in the atmosphere. 97.2% of the water in the hydrosphere is in the ocean. 2.8% is not. Of that 2.8%, 2.15 of the 2.18 is frozen in the glaciers. It's locked up in glaciers as ice. 0.62% is water beneath the surface as groundwater, and it's this thin little sliver that represents freshwater lakes, saline lakes and inland seas, soil moisture, atmosphere, and stream channels. And so it's the freshwater lakes, the saline lakes and inland seas, and the stream channels that make up running water. And so you can see it's a tiny percentage. And of that percentage, right, 0.008%, this is not even potable. We can't drink salt water. So freshwater lakes and stream channels combine to make 0.0091% of the water on the planet. So that's water that's easily accessible on the surface, that is fresh water, that is easily treated and drinkable. So you can see why water, potable water, which is water that's drinkable, is such a scarce resource. And its availability is not something to take lightly. So not only is it such an important resource that is not as abundant as most people think, at least people on the East Coast and the West Coast of California, they are well aware of its scarcity in other parts of the Western United States and of the world in general. But it's also very powerful, though, as far as how it shapes the terrain. So running water is part of the larger hydraulic cycle on the planet. So energy from the sun is absorbed by the ocean, and that energy results in the evaporation of water from the ocean. Then that water vapor is carried by the atmosphere, where it precipitates out as liquid water and falls as precipitation onto land. And then that water does one of three things. It either evaporates again or is transpired by plants going back up to the atmosphere, either goes into the ground as part of the groundwater system, or it flows over the surface of the earth as what is called runoff. And this runoff, water flowing on the surface of the earth, is what is referred to as running water. Now you'll note the total amount of evaporation over water and land and precipitation over water and land. If you add up all the evaporation, that's water leaving the surface, and precipitation, that's water coming to the surface, it's zero. So the hydraulic cycle is a closed system. So the earth is not really gaining or losing water at any significant rate. So how is water scarce? Well, how this water is distributed across the planet is not equal. So there could be an abundance of water in some locations, actually so much water that it's problematic. You have flooding and so forth. You can have too little water, where you have drought. So water's distribution is in the result where we have running water on the planet is a function of the climate. But runoff is part of this larger hydrologic cycle on the earth. So how running water behaves on Earth's surface is dictated by the topography of the surface, the shape of the surface. And so we all know that water flows downhill. So water flows in the direction of the steepest descent, or where there's the largest slope. And because of that, we have regions of the surface, which we call drainage basins, or also referred to as watersheds, where all the running water is drained out of that region by one or two main streams. So a drainage basin is a region, or also known as a watershed, is a region where all the running water is drained out of it through one or two main streams. So this is the draining stream right here. The boundaries between drainage basins or watersheds are called drainage divides. So here's the drainage divide on this side, and the drainage divide on this side, and the drainage divide at the top. Okay. So if we look at, say, the United States, the largest drainage basin or watershed is that of the Mississippi River. The Mississippi River drains all the running water from this entire region shaded green. All running water is drained in this region, is drained ultimately by the Mississippi River into the Gulf of Mexico. Now, the Mississippi River drainage basin can be subdivided into smaller drainage basins, which are regions that are drained by smaller rivers. For example, this is the Missouri River drainage basin, where all running water in this region is drained out through the Missouri River into the Mississippi. This is the Upper Mississippi drainage basin, where all running water is drained by the Upper Mississippi River into Lower Mississippi. This is the Ohio River basin, where all running water is drained out by the Ohio River into the Mississippi. Same thing for this is drained by the Tennessee River, this is drained by the Red and White Rivers, and this is drained by the Lower Mississippi River. And even those watersheds can be divided into smaller watersheds. For example, this dark shaded green, this is the Yellowstone River drainage basin, where all running water in this region is drained out by the Yellowstone River. Now, why is this important? Well, it's because whatever we do here in this region influences down here, because what we do to the running water in these regions ultimately ends up where it's drained out. So for example, if you're dumping pollutants into a stream, let's say in Western Pennsylvania, that stream carries the pollutants away, right? Hey, it's convenient to you, you don't have to deal with it. But who does have to deal with it? The people downriver, in the ecosystems downriver. And if everyone up here near the tops of the watersheds have that same mentality, and they're polluting the rivers and the streams, then all that pollution ultimately accumulates and is dumped out there. So there's many situations where this has happened. And our rivers were extremely polluted by especially larger rivers that were draining large watersheds or drainage basins because there were no environmental regulations. In the 1970s, right, rivers were so polluted that many of them you could not swim in. You couldn't even swim and go in. They're so polluted. The bacteria counts from sewage runoff and other chemical pollutants from industry were so high. It was the formation of the EPA, the Environmental Protection Agency, under the Nixon administration that started putting in regulations as to what you can and cannot dump into rivers. So I personally grew up in Western Pennsylvania, right about here. So I wasn't in the Ohio River watershed. I was in a different watershed. The running water was drained by the Susquehanna River into the Chesapeake Bay. So I was in the Chesapeake Bay watershed. And the Chesapeake Bay watershed is a relatively large watershed where all the running water ultimately drained into the Chesapeake Bay. Now the town I went to high school in year 2000, they put a sewage system in where the sewage would be pumped, so the human waste would be pumped to a treatment plant where it'd be treated and then released into the local stream. Prior to the year 2000, a lot of the sewage, if people are away from a stream, they had a septic tank. But if houses that were built years ago along a stream, the sewage was just dumped into the stream channel. So they'd often joke, you know, how far is a town away from another town? It's like, oh, it's, 20 flushes down the Susquehanna River. And the stream channel that ran behind the baseball field where I grew up, if you hit a baseball into it, it had so much pollution from the mine drainage, the coal mines, and also the sewage, that if a baseball went into it, you dare not go in to get it. So it was polluted with a lot of baseballs too. And in Western Pennsylvania, the dialect they call creeks, they call them cricks. And so it was affectionately known as the shit crick, right, from all the pollution in it. And so the thing is, not only were our streams polluted, but all the pollution that we were putting in was running downstream. And all the pollution everyone in this region was putting into their stream channels was all dumping into the Chesapeake Bay. So the Chesapeake Bay was essentially acting like a toilet for large portions of New Jersey, Pennsylvania, Maryland, and so forth. And so the ecosystem of Chesapeake Bay was suffering greatly. Remember, I was a child, there was a large public service initiative where I'd see these stickers on all over the place. It says, we all live downstream. It's trying to raise awareness that what you dump into a stream is going to go down and influence downstream. Now, that wasn't true. We don't all live downstream. The town I grew up in was actually at the beginning of a stream channel, so we didn't have to deal with anyone else's pollution. But anything that we put in the stream would be dealt with by people and ecosystems further down. But this campaign, which led to reduction of pollution of trash and sewage, it made a positive improvement. The streams began to clean up. Populations of fish, invertebrates, and other organisms that would historically occupy these ecosystems began to rebound, and people began to be able to use these streams for recreation again because they were cleaner. And so it's important to realize that what we do, what we dump into the streams, what we do influences everyone downstream. And it not only does influence, but it's concentrated. So for example, whenever farmers fertilize their fields in the Midwest, some of that fertilizer gets washed into the Mississippi River. And all those nutrients get dumped into the Gulf of Mexico. And what happens there's a large influx of nutrients, fertilizer into the Gulf of Mexico, is that the algae just blooms. There's these large algal blooms. And whenever the nutrients are gone, all this large population of algae that was supported by the nutrients dies off. Whenever it dies off, microbes that decompose it, they suck all the oxygen out of the water, and the water becomes anoxic or hyperoxic, and the shellfish and fish begin to die. And then also the remains of the algae wash ashore, continue to decay, which produce noxious gases. So the Gulf Coast of Florida sometimes has algae that washes up against it, dead algae from these algal blooms that pollutes the air from this noxious gas it releases while it's decomposing. And also the fisheries along the Gulf Coast suffer from the die-offs caused by the lack of oxygen from all these algal blooms dying off. So you have competing interests where the farmers up here, they want to fertilize their fields so they can have higher yield, but the fishermen and the people living down here are negatively affected by it. And so it's situations like this where you need government oversight because you have two parties that have two different interests, right? And they have to be rectified. And that's where agencies like the EPA come in. So the flow velocity in a stream channel is dictated by its shape. So if you take two different attributes of a stream channel, its cross-sectional area, which is its depth times its width. In this case, it'd be 1 times 10, so it has a cross-sectional area of 10 units. And then its wetted perimeter, which is the perimeter of the stream channel itself. So it would be 1 plus 10 is 11, plus 1 more is 12. If you take the ratio of the cross-sectional area to its wetted perimeter, that gives us a proxy for the flow velocity. The larger that number is, the larger the flow velocity. So this stream channel, which has the same cross-sectional area of 10 units, it's 2 deep by 5 wide, has a wetted perimeter of 9. So it has a larger ratio. So the flow velocity is larger in channel B than it's channel 1. This is because the water in the center, top of the stream channel, is further away from the edges of the stream channel, where there's friction between the water and the edges. So there's less friction influencing this water, allowing it to accelerate to a larger speed. And that's important when we look at weathering and erosion by stream channels. This is the flow velocity. So here we have a longitudinal profile of a stream channel. This is how the stream channel changes in elevation with length along the stream channel. So this is distance in kilometers, this is elevation. So the head is the beginning of a stream channel. And then we find the heads at high elevation. And then it flows down in the steep elevations of the mountains. And then as it comes down, and it flows very fast because of the large grade. And because it's flowing so fast, it can transport large particles of sediment. And when it gets down to the floodplains, it slows down. When it slows down, it drops those large particles of sediment. And so that's where we get stuff like conglomerate and so forth. And as it slows further and further, it drops progressively smaller and smaller sediment as it's flowing through the floodplain. And so this flowing water, it sorts the sediment that it deposits as it flows from the head to the mouth, where the mouth is where the stream channel opens up to a larger body of water, like a lake or an ocean. So sediment transport in a stream channel there's three types. There's the suspended load, that's usually silt and clay, particles that are suspended and carried by the water. There's the dissolved load, minerals dissolved in the water. And there's the bed load, or the larger particles like sand and gravel that are slid, bounced, and rolled along the bed. And as I mentioned, stream channels, they sort the sediment as they transport it from the head to the mouth. So heavier sediments are dropped first and transport the shortest distance, because as the stream channel, as water begins to flow, slow down as it leaves the steep grade of the mountains and enters the gradual slopes of the floodplains, it drops larger sediments. Then the lighter sediments are dropped last and transported the furthest distance. And so sediment deposition will be sorted with larger sediments deposited closer to the head and smaller sediments deposited closer to the mouth. That's why the Mississippi River is referred to as a muddy river, because it has so much sediment in it, but it's all mud, because it's a slow flowing river can only carry mud. And there's two main types of stream channels. There's bedrock channels and alluvial channels. And among alluvial channels, there's two different types, meandering and braided channels. We're first going to look at bedrock channels. These are stream channels that cut through bedrock. And they're usually found near the headwaters, which are on the slope of a mountain where bedrock is exposed. And so the stream channel cuts down into the bedrock. Where alluvial channels are stream channels that cut through sediments that have already been deposited. So we usually find alluvial channels down out of the mountains in the floodplains. So one alluvial channel is known as a meandering stream channel. And it's known as a meandering stream channel because it meanders both not only in space, as you see how it takes these turns called meanders, but also meanders in time. And you'll see what I mean by that. So this is a floodplain. It's called a floodplain because this is the plain that floods during flood stage of the river, and there's a large precipitation event. This is all flowing water, right? But this floodplain is created by the river itself, the meandering stream channel itself. So if you look at this cross section of the stream channel right here, maximum flow velocity is in the center and in the top. As this curve comes, which this curve is caused by this rock here, the inertia of the water wants to keep on traveling in a straight line, but it's turned due to the presence of the bank, of the bedrock, or the sediment. Or I guess in this case it would be sediment. And so along this cross section, the highest flow velocity is along the outside. And so this really high flow velocity on the outside is eroding this bank. And as it erodes this bank, it cuts the bank in and in more. So these are called cut banks, where it cuts these cliffs. The fast flowing water on the outside cuts these cliffs. So here you can see the erosion caused by this cutback. It's eroding this back. It's undermining this structure. On the inside of the meander, the turn, the flow velocity is at a minimum. So the water is flowing very slow, so it drops sediment. It creates these deposit points or point bars, right? Where it creates kind of like these sandy points. So here's the cliff, the cut bank, and here's the beach, the deposit point or point bar. Now, sometimes you have a meander that's so large, like this one, that the cut banks eventually cut and they connect two meanders together and form a cutoff. So then the stream begins to flow through that cutoff and abandons this large meander. Those abandoned meanders are known as oxbow lakes because they resemble the shape of an oxbow. So here you can see one of those oxbow lakes right here. So that's how these meandering stream channels not only meander in space, but they meander in time, because it used to flow over here, but now it flows through here. And so we can see examples of meandering stream channels in their floodplains. But here in Rhode Island, you have the Patuxent River, whose mouth it opens into the Narragansett Bay. The Patuxent River acts as the southern border of Cranston and northern border of Warwick. And here, this is the Patuxent Oxbows Park. You can see these oxbow lakes right here that were formed. And this cliff, this is the cut bank. This is the cut bank formed by the Patuxent River as it cut it back. So this is the floodplain of the Patuxent River. So it floods and flood stage. Here you can see another cut bank, the Patuxent River. More cut banks, and so this is all the floodplain. Okay. And so if you go down here, okay, the Warwick Mall is in the floodplain of the Patuxent River. So back in, it was in 2008 or 2010, where you had a large amount of flooding of the Patuxent River, and the Warwick Mall is flooded. It's because it was in the floodplain of the Patuxent River. I can here see another nice example of a cut bank, Patuxent River. Here's another mainstream channel, the largest meandering stream channel in North America. You can see the terrain over here, how you see this rough terrain, and then over here is rough terrain, but in between it's flat. So this is the floodplain of the Mississippi River. It meanders back and forth between its terrain, cutting it back. And so this floodplain has been widening over time. See this dashed line? This dashed line is the state boundary. So this is the boundary between Missouri to the west and Illinois to the east. Now, these state lines were made along the Mississippi River. So whenever the state line was drawn, the Mississippi River flowed along this course, and it left this Oxbow Lake, which is no longer a lake. But a lot of these sediments are rich in nutrients, and so you can see how they use it for farming. But the use of this land is mostly strictly used for agriculture. Why? Because it's in the floodplain of the Mississippi River. So whenever the river floods, this whole region is at risk of flooding. So you don't want to have structures in there because they'll be destroyed. So if you have fields where you're growing crops, you could lose the crop potentially, but at least you're not losing property. So you can see this is all the floodplain of the Mississippi River. This whole plain, it's flattened. And you're gonna here you can see these large meanders of the Mississippi River, right? As you go down further, you can see historical meanders. And here you can see the cut banks. And you can see where the Mississippi River used to move up here whenever the state line was drawn. And now it formed a cutoff. It flows through there. Once again, look, this is mostly all farmland, and you can see, some remnants of these oxbow lakes. So the Mississippi River is a meandering stream channel. It meanders. There's a very wide floodplain here. So you can see here's one edge, there's the cut banks, and here's the other edge over here. So it wants to meander through here over time throughout this floodplain. The floodplain gets larger and larger the further down. You can see these large meanders and where the state lines used to be. This big Oxbow Lake, located here. The problem is in New Orleans is that the city is built around the Mississippi River. And so because the Mississippi wants to meander, they have to build levees around it, holding the river in. And you can see this is the Mississippi River Delta. It has kind of a fan shape. Where it's semicircular, but it has this little tongue sticking out here. And why it has this tongue sticking out here is because the Mississippi River has been constrained to continue to flow out at this location, dumping sediments, where it normally would be allowed to meander back and forth, depositing sediment all throughout this region, creating this delta, this fan delta. But being constrained to this stream channel, it has dumped sediment in the same location for a long time, creating this tongue of sediment. Another type of meandering alluvial stream channel are braided channels. Now, braided channels are stream channels that flow through very fine sediment that's often deposited in the outwash plains in front of glaciers. So glaciers, the water flowing underneath the glacier, because the space between the glacier and the bedrock is so small, the water can only transport very fine sediment like mud. And that mud is deposited in front of the glacier, then the meltwater running through that mud creates these braided stream channels. They're called braided because they converge and diverge, forming these complex waterways that kind of resemble braids. And so you can see example of these braided stream channels. This is Alaska. So all the meltwater coming out underneath these glaciers have deposited fine sediment in this region, and then the meltwater flowing through it creates these braided stream channels that flow through it. You can see really here why they get the name braided stream channels. Then we have bedrock stream channels, which because they're in bedrock, they can't move back and forth, so they stay in the same location, and they just weather and erode the bedrock down, 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 creating these deep V-shaped valleys. You can see here, this is the Yellowstone River, just carving down into the bedrock. And so this creates canyons. This is how the Grand Canyon was formed from the Colorado River, carving a V-shaped canyon down through the bedrock, which is the sedimentary rocks of the Colorado Plateau. And over time, a bedrock stream channel can turn into a meandering stream channel as more and more sediment is deposited along the stream channel, and it has wiggle room. It can wiggle back and forth and cut back against the bedrock and carve a larger and larger floodplain. And so we can have what is a bedrock stream channel over time turn into a alluvial stream channel. We can see this process in the old mountains, the Appalachian Mountains here in Pennsylvania. You can see it's just the topography is almost strictly shaped by the running water. You can see all these valleys, V-shaped valleys that are carved by these stream channels. But if we zoom in on one, we can see how these stream channels, so here's the head, and it flows down. It's carving this V-shaped valley, the steep V-shaped valley. And each stream channel has a valley, it flows down. And as you go further down, you see the valley floor gets wider and wider as more and more sediment is deposited, which allows the stream channel to meander back and forth and cut back against the walls of the valley, forming a larger and larger stream channel, floodplain. And so as we go down the river further and further, we get a larger and larger floodplain where we see these flat regions in these valleys with these large flat floors. And because the topography is so mountainous here, this is often where towns are constructed, which is problematic because whenever these rivers flood, these towns are in the floodplain, so they get flooded. But you can see how this floodplain has developed, this meandering stream channel. You can see the cut banks it's formed, so it's cutting back at these valley walls over time, where you can see a less, here's a even more progressed floodplain. So this is now an alluvial stream channel that was once a bedrock stream channel. And you can see a less progressed one here. And as you go further up the stream channel, you can see how the floodplain gets narrower, 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 and turns into a V-shaped valley, right? Where this is still a bedrock stream channel because it's still cutting down through. Whereas you go down further, more sediment has been deposited, allowing it to wiggle back and forth over time and widen the valley, creating a more developed floodplain. And that concludes our lecture on running water.